And then, of course, there will be some coefficients, and especially if I'm multiplying, say, with x minus, it has to pass x plus. I'll use this relation, and that it would be important whether I have this relation or this relation. Then the coefficients of change will be different. And then in this case, we say that this is the Q deformation of the universal enveloping algebra, and the notation is like this. So here the notation is U of G, I didn't put it, and here it is U, maybe this is such a curly U to distinguish from the U used before. Here is UQ of the algebra G. Sometimes when you have more complicated algebras, not SL2 but SLN, you can have even several parameters. But that's beyond, of course, what we are talking now. Now, why this is called deformation? The word deformation wants to tell you that in effect the two things are related. And indeed, suppose that Q goes to 1, or look here, suppose that H goes to 0. Q goes to 1 when H goes to 0. What will happen? You have sine of 0 over sine of 0. Of course, you know from high school that if you have two sines going to 0, what will remain in the end is the relative thing which multiplies the both. So that will go to H. So it will go exactly to what I had before. Same here if tau goes to 0. We go to H. This is the reason it is called deformation. Because if the parameter Q, which may be even not a number, but if you recite it's a number, if it goes to 1, then I am recovering from this more complicated relation. I recover this. And I should also introduce a notation for this thing. This thing is called H in brackets with Q. This thing is this is the notation which we shall use over there. Okay. Now, in fact, it's very appropriate to say this here. This definition, how quantum groups arose. They arose because in solving some problem of the quantum integral inverse method, they were putting the operators in matrices 2 by 2. Matrices 2 by 2. You know that x plus, x minus, and h. They can be put in matrices. We have used these matrices 2 by 2. We have used this already. X plus, x minus, and h. So and then they were calculating exactly this generator, but from the model. And then they were seeing that they do not obtain h. For some strange reason, they were obtaining sinus hyperbolic of h. So they said, okay, if we cannot obtain h, then we should work with this new object, which doesn't have h in the right-hand side, but it has sinus of h. And that's how quantum groups were discovered. And then later, Drinfeld defined them in the case of arbitrary the algebra of the kind of SLN, which we discussed, and SON, and in fact the whole class of semi-simple algebras, which you are supposed to know their classification. So Drinfeld gives this definition in an arbitrary way. And then the Japanese mathematician Jimbo, which at that time worked just next door in Kyoto. He devised another definition, which in a sense is better than this because it doesn't involve taking such operators q to the degree h. Namely, Jimbo, instead of h, Jimbo introduced a generator k. And the generator k had the following properties. K had an inverse. And k commuting with x plus was giving q to the 1/2 this number h plus k, and commuting with x minus, it was giving here plus minus. And then x plus, and then he also replaced this equality, x plus commuting with x minus, he replaced by k squared minus k minus squared, and below was q 1/2 minus q minus 1/2. And then you may say, yes, are they what they have to do with each other? What they have to do with each other is the following thing. Suppose formally you say that q is equal to k to h over 4. So similar to this. So if I want to pass from the picture of Jimbo to this formal picture of Drinfeld, I just put q equal to q 1/2 h over 4, and then immediately you see that from here, of course, I go to here. And also the other kx plus minus is immediately going to the standard thing. So that's why the two things are related. And so this has the positive side that there are no such operators. In a sense, they are there, hidden in the background, but for the mathematical formulation, they are not there. Okay, so maybe I forgot. Did I forget to say? I forgot to say the delta operations here, but now I'll give them. Now, since I want this to prepare this for a quantum group, I will give the operations. I give them first in this case and then the other case, but in fact it is the same. Now delta of h is h tensor unit plus unit tensor h. This is before, as I said, in this trivial case, but the plus minus is not trivial. Delta x plus is x plus tensor q to h over 4 plus q minus h over 4 tensor x plus. And the same with minus. So in fact, you immediately see why I was putting here q h to the 4, because this operator appears here in the coproduct. So in the Jimbo version, delta of x plus, maybe there is some additional change. Okay, so in the Jimbo version, sorry, this is h over 4. So the Jimbo version is x plus minus is tensor k plus k minus 1 tensor x plus minus. Okay. Then the co-unit, of course, the co-unit is as before, epsilon of z is equal to 0 for all z, except for all z as before.